Hello, good afternoon. Good afternoon.
Good afternoon, ma'am. I guess I am only the person joined. No,
So maybe we can start.
how many people registered for this course?
I'm not sure. I think around 100 people have registered, but this is
Okay,
actually not a mandatory sessions and maybe recording is also available. That's why people are not joining. I think so.
okay.
Yeah.
So, are you KPKS PhD student or
Yeah,
postdoc student?
PhD student.
Okay.
Yeah.
So, I have done PhD from IITB only. So,
Okay. Which lab?
Professor HB Singh's lab. He retired.
Okay, okay. So I don't know.
Yeah, long back.
Yeah.
It's now
So
five,
now
six
you
years
are
now.
in which college?
Crescent University. It is in Vandalur, Chennai.
Okay, Chennai. So you are from Chennai.
Yeah.
Okay, okay. So I think we can start the session. Anyway, recordings will be available so others can see that.
Okay.
So I will share the screen. So welcome to the second tutorial session for the course Classics in Total Synthesis. So in the last week, we have discussed basic summary of the first five introduction session. That is, lecture one was about introduction, basic introduction to this course, and lecture two, which was about history and retrosynthesis. The lecture three was about history and retrosynthesis, and lecture two was about the introduction to general technical terms used in organic synthesis. And in lecture 4, we saw the total synthesis of illudin M and illudin C. And in lecture 5, we saw the total synthesis of FR9 00848. So, you were able to access this assignment, week 0 assignment, you tried?
Yes.
Okay.
Yes.
So, that professor was, you are basically from organic chemistry?
Yes.
Okay.
Basically, I'm inorganic chemist. Done my PhD in peptides only.
Okay, okay. Fine.
Me also.
Okay. So, we have discussed the week 0 assignment questions. So today we will be discussing the summary of last week's lectures, and I have selected some questions for the discussion also. We cannot discuss the week 1 assignment and week 2 assignment. Due date is still not over. So I think by discussing the summary itself, we will be able to answer the week 1 and week 2 questions. So in last class, I think Prahlad have asked one doubt regarding the directing group effect of OH in Simon-Smith reaction. So I have included that also. So basically, I will in presentation mode. So basically, this is the Simon-Smith reaction, that is alkene is converted into cyclopropane ring by using the zinc copper couple and CH2I2. So it is a carbene mediated reaction. And this is the mechanism of this reaction, that is the zinc copper couple react with this CH2 dihalo compound and form this type of carbenoid intermediate, which will react with this alkene in a concerted manner and form this intermediate, and we will get this cyclopropane ring and zinc iodide as the uh, byproduct. So here actually the OH plays this role in this case. Like here, this zinc carbenoid, which is forming as the Simon-Smith reagent, can interact with this OH, and this oxygen is able to coordinate with the zinc. So it will be directing, that is the directing ability of this particular OH group. This oxygen can coordinate with the zinc, so the CH2 will be attacking on this alkene from the same side of as that of this alcohol group. So attack take place cis to this hydroxyl group. That is why we saw that if it was a methyl group here in the alpha position and here is OH in the beta position, More than steric, this directing effect of this OH groups plays a role here, and the cyclopropane ring will be formed in the same phase as that of the OH group. That is because of the coordinating ability of this zinc with this oxygen. And now, moving on to the discussion on the last week's lectures. So, the first lecture was about cubane. So, it is a non-natural product having four-membered rings, and as we can see, there are six four-membered rings fused together. And since there are several synthetic challenges for this molecule, including the six four-membered rings fused together, and talking from the retrosynthetic point of view, there is no functional groups in this particular compound, and it is highly strained, and the molecular weight of this compound is about 104. So low molecular weight is also a synthetic challenge. And we know that this four membered ring, for the construction of a single four membered ring, we can utilize 2 plus 2 cycloaddition, that is photochemical reaction can be utilized between two alkenes to form the four membered ring. And we have also seen one particular type of dione, which and this discovery led to the development of this cubane like systems, and that dione is known as Cooksen's dione, which is synthesized from this cyclopentadiene, and this dinophile is this benzoquinone, which will first undergo a 4 plus 2 deal Salder cycloaddition to get this compound. And there will be two alkenes here, and these two alkenes will undergo a 2 plus 2 photochemical cycloaddition reaction to form this Cooksen's dione. And for the synthesis of this cubane, we have seen we were the different carboxylic acids were utilized, like 1,3 cubanes, 1,3 substituted carboxylic acids, 1,2 disubstituted carboxylic acid, and 1,4 disubstituted carboxylic acid. So before planning the retrosynthesis, sorry. So before planning the retrosynthesis, there is certain aspects that one should think about this planning this retrosynthesis for this cubane. That is how many four membered rings can be made by photochemical reaction, and about the reversibility of the reaction, and how easily the starting material could be accessed, the stability of the starting material, as well as the possibility of other intermolecular reactions. So since in a cubine there is no functional group, so one method to plan its synthesis is the introduction of a functional group. So the functional group which we are introducing should be easily removable, and it should be easily introducible also. And so for the construction of the four membered ring, one can plan of two reactions, that is either a ring expansion reaction or a ring contraction reaction. Basically, we have seen ring expansion reaction means that is from a three membered ring, we will be planning for a four membered ring. But more than that, a much easier task will be constructing a four membered ring from a five membered ring itself. So, one such reaction for the construction of a four membered ring from five membered ring is Favorsky rearrangement. So this is actually what is happening in Favorsky rearrangement. It is a ring contraction reaction. So here we have taken a six-membered ring, and we are getting the product as a five-membered ring. So what is happening? We are treating this alpha halo ketone cyclohexanol with this base. So this acidic proton will be abstracted by this base, creating a carbanion here, and this carbanion will attack at this carbon, and this halide will be eliminated. So this kind of intermediate will be forming, and next again the base will attack at this position at this alpha center of this carbonyl group, and this will be forming. And then when this negative charge migrates to form this ketone, this ring goes back to here, resulting in the formation of this intermediate, which will be abstracting a proton to get this compound. This is basically Favorsky rearrangement. That is, a base will be abstracting this proton, and this bond will attack here, and this will migrate, and that will result in the ring contraction to form one carbon less compound. So this is the main reaction that is utilized in the cubane synthesis. So we have seen this as the precursor for the synthesis of this cubane. That is, this is like we are getting one single mono substituted cubane because we are utilizing one bromide only, and from this cyclopentane ring we are constructing this cyclobutane ring by this type of quasi Favorsky rearrangement. Like same will be the mechanism. This proton will be abstracted by the base, and as a result this will attack here and this will eliminate, and then again the base will attack at this position, and this will be O minus, and O minus while moving back to this double bond, and this bond will be this will be resulting in a four membered ring. I hope this mechanism is clear. So so actually in this place of bromide, where this bromide is actually there, in that place this carboxylic acid will be forming. So here we can see there are two bromides and two cyclopentanones. So this will be resulting in two Favorsky rearrangements are possible, and that will result in this kind of disubstituted cubanes. So 1,3 bromide will give 1,3 dicarboxylic acid substituted cubanes. Similarly, 1,4 will be giving 1,4 disubstituted carboxylic acids in cubane. Then we have also seen the total synthesis of this cubane by reported by Eaton and Thomas in 1964. And in that we have seen Diels-Alder reactions also they are utilizing, and then this quasi-Favorsky rearrangement. These were the key reactions in the synthesis we have seen for the cubane. Now, the seventh lecture was about endiandric acid, and these are the structures of endiandric acid C and endiandric acid D. And so, as we can see, this one four membered ring. This is the four membered ring fused with one five membered ring and six membered rings. And this compound is isolated from the leaves of Endiandra introsa by Black's group in 1980. So the presence of this cyclohexene indicate the possibility of Diels-Alder reaction for the synthesis of this particular compounds, and these are found in nature as racemates. So this was the biosynthetic hypothesis for this particular compound, where they plan to do take a tetraene and do this 8 pi conrotatory electrocyclization to get this particular cycloocta triene, and further when this is subjected for 6 pi disrotatory electrocyclization, we will get this particular compound, and this was the intermediate for almost all the endiandric acid, and this on treatment with this on undergoing intramolecular Diels-Alder cycloaddition, we will get this particular one derivative of endiandric acid. So this first total synthesis was reported by Nicholas group in 1982, where the key reaction is this electrocyclization reaction as well as this intramolecular Diels-Alder cycloaddition reaction. So from this one particular intermediate, they are getting all the endiandric acids A, B, C and D. They have reported the synthesis of all the endiandric acid derivatives. And some of the reagents and the reactions utilized by Nicholas group for the synthesis involves linear catalyst, Glaser coupling, and as we have seen, this electrocyclization reactions. First 8 pi electrocyclization and this 6 pi electrocyclization. Then they have utilized Diels-Alder reaction as well. So this is the Lindlar catalyst. I hope you know about this. That is basically used for the reduction of alkynes to cis alkenes. So we will be getting particularly cis alkenes a lot. So this 5% palladium calcium carbonate and this lead complex along with this quinoline. This mixture is known as Lindlar catalyst. So along with this, we will be using hydrogen, and we will get cis alkenes from alkynes. So this is the use of Lindlar catalyst. And then another reaction utilized in this synthesis is Glaser coupling, which is basically the coupling between two terminal alkynes catalyzed by copper. So it is like a dimerization reaction. So that was about the lecture 7, that is the total synthesis of N-andric acids A, B, C, and D. Now, the next natural product or compound containing four-membered ring was penicillin, and the total synthesis reported by Sheehan for this particular compound have also been discussed. So, this penicillin V was discovered, not penicillin V, it is penicillin 5. So, it was discovered by Alexander Fleming in the 1920s, and it is produced by the mold of Penicillium notatum, and the structure was elucidated by Professor Dorothy Crawford. And here we can see this four-membered beta lactam is fused with a five-membered ring, and here we can also see this acylated amino group adjacent to this particular carbonyl group. So this is the beta lactam present in this penicillin. Almost all penicillin is having this beta lactam ring. This is quite unstable as well as reactive, and but in this case of this penicillin, this beta lactam does not exhibit its usual properties since it is fused with this five membered ring. So this and usually we know the amide IR ranges from 1600 to 1660, but in the case of this beta lactam, in the case of penicillin 5, they will be showing 1735 to 1765. So that is a characteristic higher value for this beta lactam ring. And for the synthesis of this beta lactam ring, various reactions have also been discussed. First one was cyclization reaction, where beta amino acids can be used for the cyclization to form this kind of beta lactam, and reagents like phosphorus trichloride, then thionyl chloride, acyl chlorides could be utilized for such cyclization reactions. Cycloaddition reactions can be also utilized for forming this beta lactam. So there we will be using alkenes and isocyanate. Isocyanate is N double bond C double bond O. So that will be utilized for the construction of this beta lactam ring. Then via ring expansion reaction means from a three-membered ring, that is acetidines, we will be planning this acetidinone synthesis. Then insertion reactions include this carbines. Using this carbene intermediate, we will be planning the synthesis of the, like, carbene intermediate will be forming, and photochemically it will be attacking on this amine, resulting in the formation of this beta lactam. So that were the reactions utilized for the synthesis of this beta lactam ring. And the total synthesis of penicillin was reported by Sheehan in 1957. So the starting materials were valine and tertiary butyl malonaldehyde. So this was the basic retrosynthetic plan for this. So this is this tertiary butyl malonaldehyde, and this compound is derived from valine. This is actually a D-penicillamine hydrochloride, this compound. So this will be undergoing a Michael addition on this aldehyde to get this particular compound, then followed by this lactamization between this carboxylic acid and this amine. So these are the key steps involved in this synthesis of penicillin, that is mycladation and mild lactonization using DCC. And other possibility of the side reaction is asalactonization. That is, as we can see here, is before this lactamization taking place, there is this NH group and this NH group. So there is possibility of lactonization with this as well. So that will give to the side reaction. That is also a major product in this case, and so that is one drawback for the synthesis as well, the side reaction as a lactonization. So this is, I have kept the mechanism for DCC coupling. So this is the structure of DCC, and this nitrogen will be abstracting this proton from this carboxylic acid, and therefore this alpha position will get activated, and it can it can attack on this carbon, forming this particular intermediate. Then our particular amine will be attacking at this position of this carbonyl group, forming this intermediate, and now this group will be eliminated as a urea byproduct, and we will be getting the couple product. That is, basically it is an acid and amine coupling. DCC is one cyclizing a reagent used for this coupling between acid and amine. Now moving on to the lecture 9, that was about tinamycin, which is closely related to this penicillin, and both are having this 4-membered beta lactam and this 5-membered ring fused with the beta lactam. But in penicillin, we have seen this sulfur was a part of the 5-membered ring, but here it is not. So this compound also exhibit antibacterial properties, and this is obtained from the soil microorganism from this Streptomyces species. So this enantioselective synthesis for this compound was reported by Merck Group, and its synthesis started from the commercially available L-aspartic acid. And then one other synthesis also have been discussed, which was a racemic method, which is more operationally simpler, which is basically starting with an reaction between enamine and ketene. So in the both case, key reaction is a type of intramolecular carbene insertion where the strained bicyclic nucleus is constructed by an intramolecular carbene insertion. So that is the key reaction in both the cases. Then another reaction utilized in this racemic method was Mitsunobu reaction, where we have seen both intramolecular Mitsunobu as well as intermolecular Mitsunobu is being used. That is basically for inverting the stereochemistry at one position. So this is the mechanism of Mitsunobu reaction, where we will be using this diethyl azo-dicarboxylate and PPH3. So this PPH3 will be coordinating first with this nitrogen of this diethyl azo-dicarboxylate, forming this intermediate. Then this double bond will be abstracting, this nitrogen will be abstracting this proton from our nucleophile, generating our nucleophile Nu minus. And then this since this oxygen have a higher coordinating tendency to coordinate with phosphorus, that will be coordinating with this phosphorus, forming this intermediate. And this will be the byproduct from this diethyl azo-dicarboxylate. We will be getting diethyl 1,2 hydrazine dicarboxylate as the byproduct. And now this particular compound, from this particular compound, our nucleophile will be attacking at the carbon center, and this pph3o, which is a stable compound, will be eliminated, that is triphenyl phosphine oxide, and we will be getting our substituted product as the um, as our product. So here basically this attack of this nucleophile is in an SN2 fashion. So whatever stereochemistry previously um, this OH is having, our nucleophile will be attacking from the opposite side of that particular OH group. So this is an SN2 reaction with the inversion of stereochemistry. So this particular reaction is utilized for the inversion of stereochemistry in the synthesis of this thienamycin. For the inversion of a particular alcohol, they are utilizing this reaction. Then lastly, we have seen our discussion on the prostaglandins. So prostaglandins are basically, this is the core structure, that is a cyclopentane ring with two side chains are there, and it was discovered by von Euler in 1930, and the structure was elucidated later in 1966. So it is a carbocyclic oxygenated C20 molecules, and their classification is based on the unsaturation as well as the functionalities present in the compound. So this PG stands for prostaglandins. So in the case of PGA, PGB and PGC, as well as other some compounds also, we can see that a cyclopentenone is present. So depending on the position of the cyclopentenone ring, it is named as PGA, PGB and PGC. Then coming to PGD and PGE, there is no double bond. But in addition to that, this hydroxyl group is present. That is a beta hydroxyl group is present to this ketone. And then moving to this PGF series, we are not having this ketone. Rather than that, we have two hydroxyl groups. And then PGF alpha and PGF beta means, in PGF alpha means this 2 OH group is in alpha position. In PGF beta means one OH group will be in this particular OH group will be in beta position. Then other compounds are like PGF alpha 1 alpha 2 alpha, that 1 and 2 subscripts indicate the number of double bonds present in this side chain. So the main synthetic challenges were the five chiral centers present in this prostaglandins, in which four are in the ring itself. And considering the F series, there are four particular chiral centers in the ring itself, and this hydroxyl group. Um, Okay, the in PGF we can see one hydroxyl group is also at the C15 position, which is away from the cyclopentene ring. So that is also one synthetic challenge. Then one side chain is having trans double bond, and other side chain is having cis double bond in the prostaglandins. So that is other another synthetic challenge. Then the first total synthesis of this prostaglandins was reported by Corey and co-workers. So basically, they planned the synthesis of this intermediate, which is very significant in total synthesis of this prostaglandins. Uh, so this is Corey's lactone, and utilizing this Corey's lactone, this Corey group have reported the synthesis of PGF2 alpha and PGE2 alpha as well. So they are starting with this cyclopentadiene, and the key reactions involved are Diels-Alder reaction, Baeyer-Villiger oxidation, and iodolactonization. So this is the Baeyer-Villiger oxidation. That is, it is actually we will be taking an aldehyde or a ketone, and it is just an insertion of an oxygen in between this side chain and this carbonyl group. So as we can see the product like this, either it will be inserted this side or in between this R2 and this carbon, and this will be the byproduct of that. So we will be utilizing any peroxy acid like MCPBA or H2O2, like that peroxy acids will be utilized, and the mechanism is that this OH group will be this oxygen will be attacking at this carbonyl carbon, forming this intermediate, and then after that it is basically a migration kind of reaction. That is, this group will be eliminating this acid will be eliminating, and either this R2 can migrate to this R2 can migrate or R1 can migrate. So that migratory aptitude depends on this particular order. Hydrogen is having greater migratory aptitude than tertiary alkyl, then cyclohexyl, secondary alkyl, primary alkyl, and methyl. So these are the main things that we saw in the last week's lectures for this five uh, total synthesis of this five natural products. So now maybe we can move to the discussion. So first, I have kept some questions from this Baeyer-Villiger oxidation. So Aravindan, can you please unmute? Hello, are you there?
Hi, 1 minute.
Okay, okay. So this is the first question. That is, it is a type of Baeyer-Villiger oxidation. We are utilizing H2SO5, and that is one oxygen will be getting inserted. We have to know the migratory aptitude here, particularly where it will be getting inserted, at this position or this position.
Answer is either B or B. Okay. Answer either C or D. I'm doesn't know about sure about the stereochemistry.
Stereochemistry is already fixed in the starting material, so there is no change in the stereochemistry.
Then answer is C.
Yes, answer is C. Because tertiary alkyl group is having more migratory aptitude, so
How many questions you have?
I have about 9-10 questions, I think.
Okay. I am the only person.
Yeah, you are the
Okay.
only person. But
Okay.
all are easy questions, like this kind of questions
Okay.
we
Okay.
have included.
Okay.
Next one is also another Baeyer-Villiger oxidation. So here, Which will be the answer? Where it will be inserted?
Answer is A.
Yes, answer is A. And next one, this is also bear vinegar. So here just we have kept the name of the product, that is phenyl 2,2-dimethyl propanate tertiary butyl benzoate isopropyl benzoate ortho tertiary butyl benzoic acid. So where oxygen will be inserted and which will be the product in this case?
Mm, not acid. So it is tertiary. Answer is B.
Yes,
Tertiary
answer is
butyl.
B. Tertiary butyl benzoate. That is, it will be inserted here.
Yes.
Then this one.
Mm, here the answer is A.
Yes, it will be inserted here at this position. And this is also bear vinegar.
Yeah, this one is familiar one, but the answer is tricky.
Yeah.
Uh, bridge head it will move.
Mm.
Then endo exo product.
Mm.
Whether
But
answer is C.
answer is C.
C.
Endo or
C.
exo will
Right.
be major.
Okay. Then answer will be. mm, mm, mm. Answer A. Shall I? I am stick with A.
Okay. So this is actually what is happening. We are getting both A
Mm,
and C, but A will be the major product with 65% of field, and this
mm,
will be an exo attack. And but this particular compound will be proceeding with this particular chair type of transition state. So this will be the major product. And here this both type of transition state is less favorable. So this is also forming, but it is less compared to this one. So A will be the answer. Is it okay?
yes, fine.
Yeah. Then this is which reaction it is?
This is like a carbene formation, like a cyclopropene formation, right? 1 minute, 1 minute.
Yeah, yeah,
Give
fine.
me a time. Mm, One side elimination. It is like Tabarsky reaction. Reaction or something else different. Suddenly, CO2
Yeah, you are on the right path.
Oh, sorry, here it's like a suddenly it's not striking.
Yeah,
OME
okay. So this is
contain.
a Favorsky rearrangement.
Huh?
Favorsky rearrangement type of reaction. That is, this proton will be acidic. So there a carbanion will be generated, and that will be attacking at this position, forming this kind of cyclopropane like intermediate. Then again this OMe minus will attack at this carbonyl carbon, and then this ring will be opening and forming this final product.
Okay. Then answer is 3,
3.
right?
Option C is the answer. So this mechanism is clear.
Yes, yes, yes.
Yes. Next, this one.
Mm. Iodolactation.
Yes.
Okay. So first one is if it is I am getting one is front, another one will be back. So A and B the only two options for me. Then so B is the answer.
B. How you confirm the stereochemistry of iodine? How it will be?
Uh, if it is say iodopropene ring formation
Yes.
happen, either it may in the upside or downside,
Ah.
then COO carboxylate ion will ring open in the opposite side. It will be favorable.
Yes, opposite direction. So the
Right?
stereochemistry will be opposite to that of this carboxyl, right?
Yes. So then I fix with that hydrogen is if it is the front side,
Uh,
iodine should be in the back side. So
uh,
that's why I have picked that B side.
but as you say, this if this carboxylic acid is attacking from this from a particular position, the
Yeah.
it will be opening in the opposite direction, right?
Yes. Yes.
So then this carboxylic that is this particular sender and this particular sender will be
I,
having opposite stereochemistry.
yes. Yes. Okay.
So
Correct.
this
Yeah.
hydrogen and iodine will have same stereochemistry then, right? I am talking
Yes.
about
There is no.
this one,
Yes. Yes. Yes.
and this one will be opposite. Fine.
Correct.
Yeah.
Fine. Fine.
So this iodine ring will be open from the opposite face of the attacking face.
Yeah. Yeah.
So option A will be the answer. And this one.
This is 1 3 sigma tropic 1 2 1 5 1 minute
Yeah.
1 3 sigma tropic 1 3 only, right? There is no methyl shift. It's like a one 1 3 sigma tropic shift only, right?
1 3
Like
sigma tropic shift. Can you explain that?
1 minute
Yeah.
1 2 3. Okay. 1 3 methyl. Are we changing 1 5 methyl? All the question were changed, right? So 1 minute.
Yeah, yeah, you can think.
Sigma methyl. It's not a one, two, one, two, three, four. Yeah, it is like a 1 5 sigma tropic shift. It's
Yes,
not a
it is
one
one
three one.
five sigma tropic shift. I have attached this one. So from this particular position, this bond will be shifting here. This will shift here, and here that hydrogen will be coming. So 1 2 3 4 5. 1 5 hydrogen shift is taking place. Then this one. I think this is the last question.
Mm-hmm. Okay,
Yeah.
there it is. What you have asked is it is like a 2 + 4 pi electron. Can't rotate it here. It is
First,
2 4
we
and
have to
5.
see 6 pi system or 4 pi system.
Yeah, it is like it is a 4 pi system because other two four electrons are not changed their position. So 4 pi electrons. Then option is B or D. Then if it is the stereochemistry, is same side. This rotation means it is would be 4 and 5 electrons. Would be is it conrotatory? 4 pi electron conrotatory exactly right.
This is actually 6 pi system because one of this bond is not involved in this reaction. See, this is remaining as such, and these three double
Okay.
bonds are participating. So a bond is forming
Oh,
here.
okay. Okay. Okay.
Fine. So it will
Then
be shifted here. This will be shifted here, and this will be shifted here. So the six-membered ring and four-membered ring can be formed by in in that way only.
okay.
Yeah.
Okay.
So it is a 6 pi. reaction, and 6 pi thermal condition which will be favorable.
6 pi means con-rotatory. 6 pi, I have to recollect. Sorry.
Yeah, yeah, it's okay. 6 pi in thermal condition, disrotatory will be favored.
Okay.
6 pi in photochemical condition, conrotatory will be favored.
Okay.
So in the case of 4 pi system, it will be opposite. If it was a 4 pi
Okay.
system, then thermal condition will favor conrotatory and photochemical condition will be favoring disrotatory. So here the
Okay.
answer is 6 pi disrotatory electrocyclization. Fine. So this also I have included for maybe you can recollect that conrotation and cis rotation.
Okay.
Conrotation
Okay.
means it will
Fine.
be same side, that is either clockwise rotation or anti-clockwise rotation of both this orbitals. This is actually for pi system, so it will be conrotation will give us the cis product in this both case. In the case of 4 pi system. And this is disrotatory, that is one will be rotating in counterclockwise and one will be rotating in clockwise direction.
Okay.
Yeah. So that's all about today's session. Yeah.
Okay. Thank you.
Much. Thank you
Thank
for
you.
joining. Thank you so much.
Yeah.
Yeah.
Yeah. Thanks.
We'll meet in next week.
Yeah.
Yeah.
Then when I will get to know the my assignment questions marks
After the due
after
date,
the
it will be available. I think for week one assignments, 8th October is the last date. So after that, you
wait.
will be able to review. So next week, you will be able to get the week one
Okay.
assignments
Okay.
and week two assignments mark.
Okay. Okay.
Yeah.
Okay. Thank you.
Thank you.
Thank you.
Ma'am, nobody is there.
No, so I will give one whole summary of the week one and week two lectures.
Okay, fine.
Okay. So in week one lecture, first we have seen this introduction about the syllabus of the course and the types of two types of synthesis, that is target oriented and methodology based. Then we have met some new terms, not new terms, familiar terms, but we have seen the definition of those terms like organic synthesis, total synthesis, semi synthesis, formal synthesis, and partial synthesis. Then we have seen the basic requirements and what is the need for the synthesis in our everyday life, as well as in our like related fields, what is the need for the synthesis of these different organic compounds. Then in lecture 3, it was the introduction about the history of total synthesis, synthesis and retrosynthesis, then the terms, disconnections, syntons, all that we have discussed. And in the lecture 4, we have seen the total synthesis of two natural products, that was illudin M and illudin C. Then, so these are the structures of various this illudin derivatives.
Can I ask a doubt?
Yeah, you can ask.
Later, you just show an example regarding the photochemical ring closure reaction of a particular compound. Uh, can you can you please explain the conrotatory and disrotatory mechanism regarding that?
Yes, yes.
Is my audio is recording?
Yes,
Or
yes, it is recording.
yeah, okay.
So this example I have taken. So this is a 4 pi system. So this ring closing will be giving us this product, that is cyclobutene ring. This butadiene will be giving cyclobutene ring. So here, as we can see, this hydrogens are in trans position. These two hydrogens, I am talking about this hydrogen and this hydrogen, and here these two hydrogens are in cis position. So we can draw that particular starting material in this way. That is this hydrogen and this particular hydrogen in cis position, and this hydrogen in trans position. Is it right? This kind of
Yeah.
representation. So in cone rotation, what is happening? We will be rotating our orbitals for the overlap in the same direction. So here we can see, for this bond formation to takes place, this two lobes should interact. Either this represented by this blank, it should interact, or this representation by this black color, it should interact. So conrotation means we have to rotate it in the same direction. That is either both orbitals in the clockwise direction or both the orbitals in the anti-clockwise direction. So if we are rotating both these orbitals in the clockwise direction, we can see this will come here, and this on rotating this clockwise direction, this orbital will be coming here. As a result, this R group will go to this position and this hydrogen will be coming at this position. And similarly, this R group will go to this position and this hydrogen will be coming at this position. Fine. So
Yeah, fine,
here
fine.
this bond will be forming, and we can see, as we can see in the intermediate, in the product, this both this R group will be in the same side and this hydrogens will be in the same side. So we will be getting this cis product as the major product. Similarly, we can also explain with this clockwise rotation. Here we did anti-clockwise rotation of both the orbitals, or we can do clockwise rotation of both the orbitals. Same cis products we will be getting.
Okay, okay. One more doubt is there regarding this mechanism. Uh, if we are saying that it is in conrotatory, the accordingly the conrotation and disrotation, the group on the particular bond will be aligned as cis or trans.
Yes.
I have a doubt that if we are incorporating a bulkier group like tertiary methyl cation or something bigger groups in this particular position, is that strain or bulkiness of the group will affect the rotation of like a conrotation or disrotation?
Yes, it can affect. In that case, we have to carry out the reaction more harsh condition, because considering this orbital approach, for this particular electrocyclization to happen, anyway this orbital have to be overlapped. This should come like this for this particular bond formation to take place. So if the more bulkier group we are using, there will be of course steric effect of that group, but maybe by using more harsh conditions, by increasing the temperature in the case of thermal reactions, or using some catalyst, that can be possible.
Okay, I'm just asking that in normal condition, if for a particular reaction to be happen like this, in the case of a 1,3-butadiene, if methyl group or hydrogen is present, it will complete the reaction in normal conditions.
Yes, yes.
Uh, for example, if a reaction undergoing by disrotatory ring closure, if I'm incorporating a larger group in the normal condition itself, whether it will be transferred, the particular reaction going through conrotatory or disrotatory, whether it will be transferred to the opposite direction due to the bulkiness of the reaction, if extreme condition is not implied.
The no, because in I will show, because in the case of disrotatory to happen, you can see the position of these lobes. Like it depends
Okay.
on the position, like which orbital is involved, in HOMO is involved or LUMO is involved. Disrotatory and conrotatory will depend on that, because in the case of thermal condition, HOMO and LUMO will be interacting, but in the case of photochemical reaction, that HOMO will be excited to a LUMO state, and that LUMO-LUMO interaction will be taking place. So the bulky group does not have any effect on changing the conrotation to disrotation. That can be controlled either by thermal condition, or that will be depend particularly either it is thermal or photochemical, or it is 6 pi system or 4 pi system. That will be the controlling factor for that. Bulkiness does not have any influence on this conrotation and disrotation. Is it fine? I hope it is fine. As I have discussed, 6 pi system on thermal condition will be undergoing disrotation, and 6 pi system on photochemical condition will be undergoing conrotation. And exactly reverse will be the case of 4 pi system. 4 pi system, On thermal condition will be undergoing cone rotation, and under photochemical condition it will be undergoing disk rotation.
Okay, okay, fine. Thank you.
Okay. So that was about illudin M and C, and this FR900848. That were the molecules we discussed in week 1 lecture. That is, both are having 3-membered rings, cyclopropane rings. Then we have also discussed some week questions from the week 0 assignment as well, where we have discussed some name reactions also, like Barton reaction, Swan oxidation, then sharpness asymmetric epoxidation, Birch reduction, and Simon Smith reaction. These were the named reactions that we discussed based on the week 1 lectures. Then in week 2 lecture, first we saw the total synthesis of cubane, and we also met this Cookson's dione, which was a major like finding for the development of the synthetic strategy for this cubane. Then we have like gone through this Favorsky rearrangement, which is another base promoted rearrangement. It is a ring contraction reaction from this 4-membered ring to no 5-membered ring to 4-membered ring, and that was utilized for the construction of this 4-membered rings in cubane from one cyclopentenone to get this one particular 4-membered ring. Then we have seen the total synthesis of endiandric acid, where the key reactions involved were Glaser coupling, electrocyclization, and Diels-Alder reaction. So here also we can see the group present is quite bulkier group. This linear chain is involved, but here also this 8 pi conrotatory rotation is happening under this thermal condition, and under this and here 6 pi disrotatory is utilized for this ring closure to form this the cyclohexadiene and this cyclobutane ring. And here we are getting this intramolecular Diels-Alder cycloaddition product, this endiandric acid core we are getting, and this can be utilized for the synthesis of various endiandric acid A, B, C, and D. Then we have seen the Lindlar catalyst and its usage in the reduction of alkynes to cis alkenes, and then Glaser coupling. And then we moved on to the discussion regarding this penicillin, and we so that for the construction of this beta lactam ring, we can utilize various reactions like cyclization reaction, cycloaddition, ring expansion, insertion reactions, and it can be synthesized from acetidines as well. Then, for the total synthesis of this particular penicillin, the first total synthesis was reported by Sheehan in 1957, and where it was the starting materials were valine derived this compound 2 and this tertiary butyl thalidommalonaldehyde, and the key steps were this Michael addition and mild lactonization using DCC, and the side reaction which is taking place in the synthesis of penicillin is acylactonization. Then this is the mechanism of the DCC coupling, that is, it is basically an acid amine coupling reaction utilizing this DCC reagent, dicyclohexyl carboxydiamide. Then we have seen the total synthesis of tynamycin, which was first total synthesis was reported by Merck Group, which is an enantioselective selective synthesis from the commercially available L-aspartic acid, and the racemic method, which was more operationally simpler, from enamine and ketene. And the key reaction in both the cases were an intramolecular carbene insertion for the construction of strained bicyclic nucleus. And then in this racemic method, we have seen that a intramolecular Mitsunobu reaction is carried out. So this is the mechanism of Mitsunobu reaction, where we are utilizing this diethyl dicarboxylate and PPH3. So it is an SN2 reaction. So stereochemistry will be inverted. And then we discussed about prostaglandins, how this naming is done for this prostaglandin depending on the functional group and position of double bonds. Then the first order synthesis of prostaglandins was reported by Corey and co-workers, And the key steps include Diels-Alder reaction, Baeyer-Villiger oxidation, and iodolactonization. So we have seen the mechanism of Baeyer-Villiger oxidation as well as its migratory aptitude. And then we have discussed some questions based on this Baeyer-Villiger oxidation, and depending on particularly the migratory aptitude of this um, side chain. And then we have seen one question regarding the Favorsky rearrangement. It is particularly happening with this kind of alpha haloketones, which is induced by a base. Then we have seen this question from iodolactonization. So here basically this iodonium ion will be forming, and uh, this OH minus will be O minus. That is, this will be able to abstract proton from this, and it will be O minus. That O minus will be opening this iodonium ion from this position. So here it will come iodine, and therefore either A or B can be the product, but considering the stereochemistry, this attack of this O minus at this position will be on the opposite side of that of the ring opening of this iodonium ion. So if this is attacking from beta phase, iodonium ion will be opening from the alpha phase, and iodine will come at the alpha phase. So this will be the product. Then for this particular sigma tropic shift, we have seen this here is 1,5 hydrogen shift is happening. Then we have also seen this particular example where 6 pi disrotatory electrocyclization is utilizing. So as I said, 6 pi in thermal condition disrotatory will be favored, and in photochemical condition conrotatory will be favored. And for the 4 pi systems, thermal condition conrotatory will be favored, and in the photochemical condition disrotatory will be favored. And this was the example we saw for the conrotatory condition. That is, our rotation will be on the same side. Either both orbitals will be rotating in the clockwise side, or both orbitals will be rotating in the anti-clockwise side. And this is the disrotation. That is, one orbital will be rotated in the anti-clockwise side, and the other orbital will be rotated in the clockwise side. So that will give us this product. So that's all about today's lecture. Um, I hope everyone is clear about whatever we discussed in this session. If there is any clarification needed, you can ask in the next session, or you can post in the doubt sharing session in the NPTL portal under this course. I will be happy enough to answer your queries and doubts in the next session. So thank you. See you in next class.